Our topic for today is plane curves and parametric equations. So let's write the definition first, and then we'll talk about what is really meaning of this. So definition: if f and g are continuous functions of t on an interval I, then the equations x equals ft, y equals g of t are called parametric equation. Equations. T is called parameter. The parameter. The set of points f of t, g of t, when t belongs to the interval, is the graph of this equation. So here is the example. We'll label it there as number 8. Like this. X equals t squared plus t. Y equals t squared minus t. T belongs to negative 3 to 3. So I think that this example will help us to understand what's going on here, and also why is it important? Why do we need it when we already have couple of other ways to describe curves. So let's recall our different methods to define a curve. So this is the new one. So before we start analyzing the examples, one of them is explicit. So ways to define curves. So far. Explicit, like y equals x squared. What is it that makes it explicit? Because y could be calculated explicitly given value of x, you just plug it in. Then it's also implicit, like in ellipse and all that. It's not just, so it's a circle, x squared plus y squared equals 9. So y is not separate, y and x are not separated, one left, one right, they are just mixed up. So when I give you the value of x, you need somehow to calculate the value of y. Sometimes that's easy, sometimes that's more complicated. The schema here is, but in both of these ways, you start with x and you get y. What happens here is actually we have a parameter t, and t can give us both x and y. Why is that important? That's particularly important for physics. So best intuition about t is to be time. So t, time. So generally there is a motion, and at every moment t, we calculate x coordinate of our position, y coordinate of the position, and record the point. So this is more realistic for physics to describe trajectories of motion. What else? For explicit functions, if you remember, they are very specific because they have to meet vertical line tests. So if you want to draw something like this, forget explicit function because it just, you cannot describe this unless you want to cut it into pieces and then describe each of them. So, so T also gives us the chance to describe some functions that do not meet vertical line test. And also usually when we look at the graph for explicit functions like y equals x squared, usually we see like things go from left to right. Here you will see motion that goes sometimes left, sometimes right, sometimes up, sometimes down. So we have much more freedom to describe different curves. All right, so I hope now we have motivation to describe what's happening here. So what do we do generally? And the easiest thing probably is just to make a table of values. We can do that using calculator as well. In the beginning, we'll just do it with, by hand. So here is t, and then here's the value of x, and here's the value of y. So which values are reasonable to plug in? Let's say -3, -2, -1, 0, 1, 2, 3. That's standard integer values. And of course, if I'm particularly interested in something, if something looks strange, I might refine my search a little more. So when x is -3, what do we get? 9 minus 3, so x is 6. And then 9 plus 3, y is 12. When x is -2, we'll get 4 and -2, so x is 2, and the y is 6. When x is -1, we get 0 here. And y is 2. Then when x is 0, they are both zeros, obviously. When x is 1, we'll get 2 and 0. When x is 2, we will get now the other way around. Actually, what was before y is now x, so it will be 6 here and 2 here. So they kind of switch the rows. And at 3, we will get 12 and 6. So then what? How do we draw this? So see, so we still draw x and y, but generally there's a timeline here. So you can sometimes put a timeline just psychologically. So what happened here? Let's say that this is 10 and this is 10. So just to give us the launch. So what happens? So in the beginning of the story, we are at 6 and 12. So 6 and 12 is somewhere here. So 6 and 12. Let me give them the names: A, B, C, D, E, F, G. So here's my point A. Then what happened after that? Position for B is much more to the left and down. So generally it's like 2 here and 6. So this is position for B. Position for C is 0 and 2. So here's the position C. Position D is 0, 0. Position E is 2 and 0. So it's symmetric here with respect to 45-degree line. Then it's 6, 2. So 6, 2 is here somewhere. And then 12, 6 generally here. So we have symmetry here. A and ABC. This is D, E, F, G. So generally we see that our graph goes like this. And then I'm not sure what happens here. So it looks like this probably. And this is the direction of motion. So we started at A, we moved here. It might be a good idea here after C to have a little refinement. So maybe here to say what happens. Or here, because of the symmetry, let's say here I'll also check point when I have 1/2. So at 1/2, I would have the what? So put it on the side. So when t is 1/2, then x is 1/4, 3 quarters, and y is 1/4 minus -1/4. So x is 3 quarters, so it's somewhere here is that extra point. The same way there is an extra point here. So generally nothing dramatic, just a little wave here. So here is our motion. And basically what? I made a little error drawing here. I cannot continue here. Why not? because it says just between -3 and 3, so I have to start here. So it's just the segment that I wanted to draw. So here it is, our motion started here, and then it went all the way here, it ended up here. And then what? There is this common kind of tendency to kind of say, all right, but can I express this? Just can I express y as a function of x? What would that be? Generally, if you wanted to do that, you want to start with x, so you need to reverse this connection. So you need to solve t in terms of x, and then plug it in and get y in terms of x. If you can succeed that, I don't think that that's a healthy tendency. Just I wanted to say that that's possible sometimes, but I wouldn't really insist on it. So just to show you that that's possible sometimes, because don't try to avoid this new type of description of a function. It's actually much more dynamic and much more interesting than what we know from before. So let's learn it. Particularly, this is important because this whole chapter in Calculus 3 will be about these parametric curves in 3D. So it's really important that we learn this properly. How would the elimination go here if I need it, as I said, if I want to eliminate implicit, not explicit, implicit, to eliminate t, what can I do? I can, for example, subtract to get rid of t squared, so I get the following: x minus y. When I subtract, t squares cancel, equals to 2t. So from here, t equals x minus y over 2. So if I plug it in, I'll get the following: x equals x minus y over 2 squared plus x minus y over 2. So I just replace it here. So here's the equation that just has x and y. This is implicit function. By the way, what can I do? I can get it on the other side, maybe. So maybe multiply by 4, because there's water here. So if I multiply it by 4, I'll get 4x minus 2x, so I'll get 2x plus 2y equals x minus y squared. And then if you really want explicit, of course, you cannot get one function because that doesn't meet vertical line test. But if you square it and then solve quadratic equation, you will get y, but two separate functions. So this is a way to eliminate t. As I said, it's much easier and more natural to draw in terms of t parametric than try to avoid it. And that's basically, that's what we want to learn in section 10.2. We want to see how to parameterize some curves that we are interested in, very often in mathematics, and then also how this could be obtained. So here is one thing where knowing parametric equations could be useful. Let me consider the following problem. Using calculators, example. Use calculator to draw the graph of the parabola. Parabola is x equals y squared. So we studied that in section 1. So basically, that parabola is, however open it is, parabola opening to the right. But unfortunately, this is not a function, so you cannot draw it using the functional mode. But here's what you can do. Because here is x is a function of y, and you don't have that type of mode in your calculator. But here is a very easy thing that you can do. Since y is good in expressing both of them, then I can say the following. Okay, so what is y in terms of y? Y is y, and x is y squared. So both coordinates are expressed in terms of y, and then what? So generally, I can think of y as a parameter, which is the same as, just to emphasize that and make it acceptable by calculator, I'll call y to be t, and then x will be t squared. And now if you use a calculator, I will show you in a separate part how to do that on the calculator. If you go into parametric mode, then you can draw this parabola without any problems. Of course, the alternative would be to solve for y and get y was plus or minus root x, then to draw this function and this function, and then look at them together. Here is the most important, couple of most important examples, and that are among the main reasons why we study all this. And that is, let me erase all this. Actually, we know how the equation looks like, so I don't need to keep this. So the most important curves that we analyze in pre-calculus and in calculus, I would say, are line and the circle. So let's see how do we do parametric equation of a line. So let's see the following. Not only line, we want to see something that's even more interesting, something that we couldn't do elegantly in calculus 1 or in pre-calculus. Let's describe the line segment containing point A with coordinates 1 and 3 and point B with coordinates 5. So I want this segment. I don't want the whole line. I just want this segment. So here it is. One way to think of this, and not to do slopes and all that very complicated stuff on pre-calculus, is the following. To express, to actually imagine that we are moving here between A and B. And then basically your equation really catches that motion. So you say x equals y equals. So imagine that I start at 1, 3. So I say the following. All right, my starting point is x is 1, y is 3. And then when the time elapses, so generally that's when time is 0. So time goes, I want to do it in 1 second. So if it goes for 1 second, 1 second later, where do I want to be? I want to be 4 steps to the right, because this is 4 to the right and 2 up. So generally what you say here is the following. You say, all right, so here is 4, here is 2, and then here's t. So when time elapses, so what will that t do? First, it will make it a linear function, so it is a straight line. And what else? When t is 0 in the beginning of the story, that part has no influence because both of them give us 0, so we will be in 1, 3. And then we go at the same rate because the velocity, speed of this motion is constant. So what happens 1 second later, we exactly do what we wanted. 1 second later, we'll move from 1, 4 steps to the right and make it to 5, and 2 steps up from 3 to make it to 5. So when t is 1, I will be at 5, 5. When t is at 4, and 0, it will be at 1, 3. So those 4 and 2 are actually 4 and 2. You just subtract b and a coordinate. Look how nice it is. Of course, I should say here t goes between 1, 0 and 1. Of course, if you want longer segment, then you will take a longer time interval. So this is important how you parametrize lines. What about circle? So let me find the equation of a circle of radius 3. And then here we need something that you study in trigonometry, and that is our parameter will be actually this angle in radians. So this is your t. So t is the angle in radians. So that means when t is 0, it will be here. So t is 0 here, t is pi over 2 here, t is 3 not the pi here, t is 3 pi over 2 here. And then of course we can rotate them more than once. So t is the angle in radians. And then basic trigonometry tells you basically that this arc length here, because radius is 3, this arc length is 3. That's the famous formula for arc length. So arc length but what we want is not arc length. I want x and y coordinate. So this is my x coordinate. This is x coordinate. And this is my y coordinate. And since this is 3, then x and y are easy to calculate. And that's exactly what gives you position of that moving point M. So what is x? X is 3 cosine t. Y is 3 sine t. Here it is. Because why? Because x over 3 is cosine t, y over 3 sine t. We solve for x and y. Here it is. And then t goes as long as you want. If you want whole circle, it will go 0 to 2 pi. If you want just half of it, it will go 0 to 2 pi, and so on. So here is the radius, and then you have cosine t and sine t. And then you will see in the homework that there are many variations of this one. So for example, what if you want to start here, not here? What if you want to go faster? Because here, what you are doing is actually you are traversing this with a speed of 1 radian per second. So in 1 second, I will be 1 radian away. So time and the angle are the same, different units, but numerically the same. So you read 1 second, I say 1 radian. You read 2 seconds, I say 2 radians. And then 2 radians mean particular position and particular arc cover. And then of course, you can go with higher angular speed. So this is angular speed. Is 1 radian per second. So t is at the same time angle, but at the same time it is time, angle in radians, also time in seconds. So how many seconds, that many radians, that's why I go 1 radian per second. But if you want to go faster, then you can go like this. X equals 3 cosine 2t, y equals 3 sine 2t. This is the same circle, but just you cover it twice faster. So the speed now is 2 radians per second. And then if I go between t and 2 pi, what will happen? In the first pi, I will cover the full circle. And then I'll cover it once again because I go twice faster. So this is important for circular motion in physics. So segment and circle are definitely the most important curves to kind of learn how to parameterize. And then we'll play with the variation of this one, for example. Let me look at the following one. Here's one example. Maybe it's good to keep that in mind. And then a variation of this one. And that is, so draw the following graph. Example. X equals 3 sine t. Y equals 4 cosine t between 0 and pi over 2. So what is this? And generally, I will give you the rule at the end of the story, but it might be a good idea here just to make a table like I did a minute ago, and then see what happens. So I'll go with a little shorter table, because what happens, I know that this is something like circle. Whenever I see cosine and sine, not being squared or anything like that, I know it's some type of circle. Although, you notice that here is 3, here is 4. So generally the radius of that circle is not constant. So probably it's going to be some type of ellipse. Although, what I'm not sure is where is it going to start, where is it going to end. So it might be a good idea to just plug a few values, t, x, y. When t is 0, I get x to be 0 and y to be 4. When x is, let's say, pi over 4, then x will be 3 root 2 over 2, y will be 4 root 2 over 2. When x is pi over 2, which is the end of the story, then the other way around, x has the full value 3, and y has a minimal value of 0. So generally what happened is, I will start here at 0, 4. That's point A, B, C. And I will end up at 0, 3, and I will be somewhere there. Here's point B. So generally what happened, and this is the motion. So here is 4, so here is 3. So what is this? This is 1/4 of an ellipse. And then, so you can use also calculator to see that. And generally, there are a couple of ways to see that this is 1/4 of the ellipse. One of them is, I can eliminate the parameter. But the elimination of parameter works a little different than before. I'm not going to solve for t, I will eliminate it, and I want to use that sine squared plus cosine squared is 1. So here's what I'll do. Let's say x over 3 is sine t. Y over 4 is cosine t. And then I square them and add them up, so I get x squared plus y² squared is sine squared t plus cosine squared t, which is 1. Now I hope you recognize the ellipse. X squared over 9 plus y squared over 16 is 1. So this is an ellipse where the major axis A is 4 and B is 3. So here is that 4 as a major one, here is 3. And then, but this just says it belongs to this ellipse. But then we also see, since we are in the first quadrant, x and y must be positive, so you cannot be in the first quadrant. So it's quite obvious that it is this part. So when we have sine and cosine, then also there are ways to express the ellipse. I can actually do this a little differently and connect it with a little knowledge of trigonometry, connect it with our main example that I gave you a minute ago. Let me copy it here. So x equals 3 cosine t, we did that a minute ago. Y equals 3 sine t. That's the most canonical one. That is a circle. Starts here, radius 3, and goes counterclockwise. So that's the canonical example. What happened here? 3 and 4 are here, so that means one of them is stretched, and that's y is obviously stretched. But also cosine and sine are flipped. So how can we actually notice that, react to that, even without eliminating parameter? Here's what we can do, but that's a little knowledge of trigonometry. So x equals, I can write sine as cosine of pi half minus t. And y is, because sine of the angle is cosine of complementary angle. And x is what? Y is, I can write it the same way for sine of pi half minus t. So if I look at my main equation, what did I do here? Besides that little stretching on y, I actually did the following. My start time when t is 0 is not 0, it's pi over 2. So that's why I don't start drawing here. My start time is pi over 2. So start at angle pi over 2. And what else? Since I'm subtracting now t, I'm not going counterclockwise as normally I'm going clockwise. So start, so conclusion, start at angle pi over 2, move clockwise. And that's what I did. Pi over 2 angle is here, that's where we started at A. and then we didn't move counterclockwise, we moved clockwise. We stopped when the angle went back to 0. So that's another way to see this. So there are different ways to kind of graph curves in parametrics. All right. And then the following example. So I'm not going to analyze it in too many details like I did in my note, but just comments. So next example, instead of t has 2t. So as we announced in that analysis with the circle, what will happen? So it will start, so what would that be? We can do the same analysis. So erase it now. We'll erase this and draw it a little faster. So what will happen in the beginning? So let me draw a few values: t, x, y. So when x is 0, what happens? X will be 0. 3 sine 0 is 0, and y would be 4 cosine of pi, which is negative 4. So generally what happened is that it will start 3 sine 2t 4 cosine 2t when t goes between 0 and pi over 2. Alright, so at 0, y will be, I don't know why I wrote cosine pi, or 4 cosine 0, which is 4. So it will start at the same point A. And then what? When x gets into, let's say, pi over 4, so I'm going to get quicker. When x is pi over 4, when t is pi over 4, x will be 3 sine pi over 2, and that will be x will be 3, and y will be 0. So at pi over 4, we are here at 3, 0. So generally it's the same spot as before, but we just arrived at there twice faster. And then when we get into pi over 2, which is the end of the story, then x will be 3 sine pi, which is 0, and y will be 4 cosine pi. That's where I started the story, which is minus 4. So what will happen? We are moving, starting at the same point, but we are moving twice faster, so we will cover twice a longer arc. So we will actually end up here. So since we are moving twice faster, we are moving on the same ellipse. Why? Because when we eliminate, we'll get the same equation: x squared over 9 plus y squared over 16 equals to 1. So we stay on the same curve, but the difference is we are moving twice faster. We don't cover just a quarter of it, we cover half of it. So that's the only difference. All right, here is next example, just to review something that you mentioned. We want the following example. Find the equation of the line containing point A 1, 4 and B 5 minus 3. We already analyzed a similar problem a minute ago. So what was the story? So A is 1, 4, which is here, and B is 5 minus 3. But a minute ago we were doing the segment. Now they just want the whole line, so that means we won't restrict. T will go negative infinity to infinity. So most reasonable is to start here and go down B, or start B, or start at A. So start at A, so x equals, so y equals. So I have 1 and 4. And here's t. So that definitely says, but now I also need some numbers here. So this guy will for sure start at 1,4 because when plugging t equals 0, I am at 1,4. And elimination will tell you that this is linear function, so I'm making a line. The only thing I need is to make it sure that I'm not going to miss p. So what should I do? I should do the following. I should move 4 steps to the right and 7 steps down. Because between 1 and 5, 5 minus 1 is 4. And minus 3 minus 4 is minus 7. So I put here 4, here minus 7. I'm done. Let me see. Let me check my work. When t is 0, I'll get what? 1, 4. When t is 1, I'll get 1 and 4 is 5 minus 3. All good. What is the interval? T goes between what? Negative infinity and infinity, because we don't want just this little segment, we want the whole line. So that's the answer of what we already discussed. All right, a couple of nice examples of this. So one example that covers an interesting motion that you already saw in some math course. Let me erase all of this. Is the following example. We fire a projectile from the ground with the initial speed of 60 meters per second. At an angle of 60 degrees, which is pi over 3, of course. Find the equation of the trajectory and the place where it hits the ground. Where it hits the ground. This is a famous problem of the projectile motion. In Calculus 1, you studied just vertical projectiles, those that go straight up or straight horizontally. This is the projectile that goes at an angle. So here's this is x, this is y. That projectile is fired at an angle of 60 degrees. So initially, so here is the initially how it will be launched. And what will that do? Actually, we know at that motion, our equation is like x of t, y of t. So what happens is the following, that initial speed, initial position is here, so here is a 0 and 0. And then this initial speed of 60, so that's speed, it actually kind of splits into one component that goes horizontally and one component goes vertically. So horizontal speed, so if you continue 60 meters per every second, then part of it, sideways, then part of it, because this is your angle, is also 60 degrees. 60 degrees. So part of it, which is 60 cosine 60 degrees, which is 60 times 1/2, is 30. That's what we call x component. So V0, initial speed, x component. And then 60 sine 60 is 60 times root 3 over 2, which is 30 root 3. That's V0, y component. And that will actually, and then if you move along the straight line, that would give you what x would be 30t. And this would be plus 30 root 3. So what is this? This would be the motion where basically every second you cover 30 60 meters. So it is metric system. So 30 meters horizontally, 30 root 3 vertically, altogether you cover 60 at that angle. That would be true if this was done without any additional forces. But while moving, this projectile also feels the gravity force. And gravity force does not influence x component, it just influences y component. And I assume that you are not surprised that it pulls us down, and that pull down is negative 4.9 t squared. That's exactly the same component that we had in that vertical projectile motion in calculus 1. So what happens is it won't go straight like we thought. It will be like this. It will actually start bending, and at the end it will hit the ground. And that's the equation that they want. They are asking us, when will this hit the ground? So here is the equation of the motion. And then when will it hit the ground? Obviously it hits the ground. Hits the ground. That means that y of t is 0. So we'll set up 30 root 3 times t minus 4.9 t squared equals to 0. In general, this is quadratic equation. Luckily, we fire the projectile from the ground, so that constant term is not there. That gives us a chance to factor out t. So we get t times 30 root 3 minus 4.9 t 0. When you solve this, it's either t equals 0 or 30 root 3 equals 4.9 t. T equals 0 is just the moment. When were we on the ground? Here. So that's not what we are asking for. So next time when we are on the ground, this is the moment. So we see that t equals 30 root 3 over 4.9, which is approximately, okay, in my notes I took that. This is not 9.8, to be 10. All right, so 30 root 3 over 4.9. Okay, that's whatever value that's it. So you can put this in the calculator. I'm going to stop if you know to calculate it. But, so what's the answer? It says place where it hits the ground. So that question is actually x coordinate. So that moment, let me call it t0. So now they want answer. They want x of t0, which is what? 30 times t0, which is 30 times 30 root 3 over 4.9, which is what? 900 root 3 over 4.9. And I got in my notes 180 root 3, and that would be true here. But with 4.9 it will be a little different. So just use calculator for approximate. All right. As I mentioned, we'll do a separate video explaining how to use calculator to draw parametric curves. And then one more famous example for the history of the calculus, and that's cycloid. So what is cycloid? It was a big thing in the history of mechanics. Sometimes, what was that? Beginning of 17th century. So cycloid is an interesting curve. So cycloid, it looks like this. So we have the whole story starts with a circle. So imagine a lucky event that you get a nail in your tire. Here's the nail. And then what happens with that nail while you are driving the car? So generally what will happen, here is where the nail was in the beginning, and then while the car moves, the nails goes higher and higher, and then back down to the ground, and so on and so on. And generally this equation is the equation of the cycloid. So people derive that equation as equation of the cycloid. So the name of this curve is cycloid is x equal at minus a sine t, and y equals a minus a cosine t. So generally what happens, y part is purely periodic with a period 2 pi. So while you make one rotation, this will go at t equals 0, it will be height 0, and t equals pi over 2, that will be the highest because this is 0, so you will get to a, and then so that's actually what when t is negative 1, it will be 2a. So here is a, and that's when t is pi over 2. When t is pi, it will be 2a. When t is 3 pi over 2, it will be a again, and then 2 pi, it will be 0 again. And then you keep repeating and repeating, and x has also periodic part, but also has this at, which is progressing to the right all the time, and that's actually formula for the arc length. And generally, so how will this go? So here is the equation of a cycloid. When we do parameter, we record that, so t, x, y. So let's say when t is 0, what do we say? X is 0 and y is 0. Then when t is pi over 2, x progresses here, so it will be what? A pi over 2 minus a. Because pi over 2, this is a pi over 2 minus a, and y will be just a. That's this point here. Then at pi, x would be a pi, y will be 2a, and that's point B. And then at 3 pi over 2, x would be what? 3a pi over 2 plus a. That's what we're going faster. Plus a horizontally, and the y at 3 pi over 2 will be just a. That's that point C. And finally at 2 pi, x would be 2a pi, and y would be 0, and that's a point T. And then, as I said, the whole picture gets translated just with extra 2 pi a, because this here is 2a pi. So here is 2a pi. Here is another 2a pi. Here is another 2a pi. What is that, by the way? This is just circumference of that circle. So generally, that circumference of the circle was x. So x progress of your nail is actually the progress along the circle, but circle that moves on the straight line. So that's why that circumference was kind of opened along the. So imagine if this had some color, then while your tire or while your wheel makes one full rotation, then that color will actually print itself all the time down, or its letter N, you would see N here all the time, and that's exactly until the whole circumference gets lined up. So that's why on x coordinate we get circumference on the circle, and then y coordinate kind of fluctuates up and down. So this is another interesting example. So that's called cycloid, and then here's the equation of a cycloid. Let's say if you want one cycle, then it would be 0 to 2 pi. That would cover one cycle of the cycloid.